So test. YouTube is not receiving information and Twitch is. So let's check to see if YouTube is at least getting the stream. It always takes a few moments to my channel. Videos live. Okay, this is not week 9, so I'm going to update the title. Let's see, nobody else is there? Okay, and so Twitch, I assume. Twitch always seems to work, so let's go to my channel, manage videos. This is not week 9, this is week 11. Week 11. We will be discussing, here, I can do this on screen while you watch. There's nothing proprietary in here, and we'll see if anybody shows up in the meantime. So, FAANG Interview Study Group Week 11, powered by Restream. That's true, it is. Week 11, we will be discussing concurrency, multithreading, and distributed systems architecture. Oh, and I should log out of Slack because I don't want to get pinged. Close window. Slack. Close now. File. Quit Slack. There we go. Multi-threading. Okay. And distributed systems architecture. We will save that. Close that. And see, we've got one person here who's arrived. Is that Rajat? Rajat's always here right away. But maybe it's somebody else. Or maybe that was me. Maybe it was me because I was watching myself. Anyways, this is recorded, so anybody who shows up late can... Oh, it's Josh! I was just hoping to hear some news about how things have gone for you over the last week or so. But again, you can tell me later, but I'm just really excited on that front. And I enjoy that part of the week, is just connecting. No news yet. Okay. But I suppose no news is good news, because we know it's not done. Right. Okay, so how did that one go? I guess that was the system design, right? Very exciting. Both had system design. Okay. Oh, we'll see. Okay. Stay calm. And then, yeah, it's true. It's true. And it's like, yeah, I'm not good at holding my emotions in. They ran out of questions. Ooh, that sounds good. Did you, now here's the thing. Did you have questions for them while you were there? That's good. That's good. Yes. Excellent. That's good. That's good. You feeling good about it? You excited? I'm excited for you, even if you're not, but I want to get a sense that you're happy. Yeah. Good. That's excellent. Yeah. I know what it's like. Oh my God. I tell you, I thought I nailed the Zynga one. Remember that one? That was like in week 2 or 3. I had that Zynga interview, and I wrote the test, and then and then they just walked away at that point. I was crushed. So Oh, I was I was really crushed. It just, well, that's okay. I am happy now. So, hey, that's right. Crying robot. I am happy now, so it's fine. It's fine, but like at the time, and it is really hard to have any sense because we have to be optimistic. And so, what is the other option? So, anyways, we'll see. Yeah, yeah, and right. So that's the thing. And I remember it was, I mean, 6 years ago now, probably when I went on the Amazon one. I thought I had it. I thought I had it nailed down, and I wasn't prepared emotionally for the possibility that it wasn't going to go forward because I don't know. I just had my had it in my head that I was pretty hot shit anyways, and so what are you going to do? You're going to, of course you're going to take me. I'm kick ass. And like that kind of took the wind out of my sails for applying to jobs for like, well, for years afterwards. And that's the kind of thing. So how do you manage your emotions if you don't get a position that you really want? And like that's a question, and that's something that we have to think about as people. Like what do you do? I think the one thing to do is 2 years ago I had one I really wanted, got really excited after losing. Yeah, and that's it. And you just stop and you just can't emotionally work yourself back up into the state to say, fine, on to the next one. So the only thing, and we talked about this back in like week 2 or 3, because there were a couple of articles about how to deal with rejection at that time, and like keep it in your head to ask for John. How are you? Oh, it's good to see you. Unfortunately, so for Josh and the others, here's so. Unfortunately, I have something that's broken on the YouTube where it doesn't pop up the text on screen. So John is saying, "How do you manage my emotions when you lose?" He says he convinces himself that he didn't want to work there anyways after the interview. So that's a good that's a good strategy. The only other piece of advice that I would put in at that point is, yeah, yeah. Afterwards, you just say, "Oh, well, that was a shitty place that I never wanted to work at, anyways." Which, in fairness, I did that about Amazon, but well, kind of. Anyways, so the one piece of thing is make sure if it doesn't come around, ask for detailed feedback. And a lot of places won't do it because they're scared of the legal liability. Then there he is. Here he is. John's come over on Twitch. I really want to fix the YouTube because for the next round, because this course ends in about 2 weeks and I have another one planned. But for the next one, I just want to keep it all in one place. And so I want to get YouTube working. Anyways, ask for detailed feedback because that's how you're going to get better. Even though a lot of places don't provide detailed feedback because they're worried about the liability. But if you get that feedback, it should be valuable in terms of helping you grow and helping you move on to actually get the next one. So, so John, what this course is, I'm so happy that you've come along. This is really great to see you. So we're on week 11, and it is, let me show you what it's based on. I don't know if you've seen any of this, but this is codinginterview.com, and there is an interview roadmap. So we've been following along with this and studying the... we're going to open that link in a second. So we've been studying sort of how do you go through all of the stages of getting ready for a coding interview, and it's sort of study your algorithms, study your data structures, study your, it's actually like 8 weeks of leak code and then system design interviews and concurrency concepts. Object-oriented programming is going to be next week. So this week we're talking about multi-threading and trying to learn a little more in detail about that. We're going to be talking about thread safety. We're going to briefly look at some of the potential questions around this. I think these are rarer questions to see in a full-fledged interview. But I did want to also, there was a great talk in here about distributed systems. So that's what the week is, and sort of as things come up, we can discuss them. I've tried to fill about an hour and a half's worth of content, and so it'll be hopefully good for discussion. And so here, let's see what Josh is recommending here. A system. Here, subscribed. I am subscribed to him, so it's a bummer. It's so hard to get feedback because liability. Yes, yeah, because the liability. How they're. Yeah. So, sort of like, but it's so hard because you're representing your business, right? And so, you don't want to get sued, but the people who are asking, and if you do it on a phone call or a video call face to face, then that kind of, unless they're recording you, it kind of offsets that. So it's good of you to do that. So, yeah, so this guy, so we're going to save this as a recommended resource. I'll add that later. So the first one about multi-threading that I want to start with is this guy, because he's just a 6-minute video, should give us a brief introduction to what multi-threading is and, just getting our heads around what we're talking about it and what it means. The next guy is really cool too. So go 1.5 and play.
Hello folks. Today I want to talk to you about multithreading. At a very high level, I'm going to go over what it is and why we want to use it. I wanted to create a video on multithreading because if you're new to the concept of multithreading, it sounds really scary. In reality, multithreading is a very practical and straightforward concept. In short, multithreading enables us to do parallel computing efficiently. Let's start our explanation of multithreading by first discussing how a process works. When you start a program, it is first loaded and given an address space in main memory from your hard disk. After being loaded in memory, it is then scheduled onto an available CPU. When a process is scheduled onto a CPU, the process instructions are executed sequentially. Take, for example, this simple program which prints out "Hello World" to the console. When we run this program, the CPU will execute each line of the program sequentially, and it will keep track of which instruction it is about to execute by using what's known as a program counter. The program counter represents part of an execution context. An execution context is the current state of a running process, which includes data like what instruction the CPU is currently executing. If you have multiple CPUs, and even in the case of a single CPU, you could have multiple execution contexts within a single process. We refer to these execution contexts in an abstract data structure called a thread. A process can have one or more threads. These threads can execute simultaneously on multiprocessor and multi-core systems and execute different sections of the program. In contrast to a thread, a process is allocated an address space. In the case of a thread shares its parent process's address space along with any other threads that the parent process has created. In this way, threads are considered a lightweight option to a process because they will almost always consume less memory than a new process would. In this diagram, we see that
So I watched this the other day and it seemed a lot more understandable. Are you following along with this okay? I imagine John is up to speed on this because he's been doing this for a while. Really test how well, yeah. Okay. Well, I mean, that's why we're doing this together. And I'm already saying that this guy's probably happening in the wrong place because, maybe we should watch this in, let me let me stop this one. I'm not. It's not. It's a little more intense than I expected it to be, or than I remember it being. I don't want it to be the first one anymore. I'm gonna go ahead and I'm gonna jump to this one. This is a first year concurrency course. I promise that I have actually watched most of all of these, so I know what I'm doing. But like, is this the guy?
Hi, welcome to our concurrency unit in operating systems. We're trying something different here, which is have you watch lectures at home, and then we'll work out homework-style problems in the classroom. Let's get started. We'll start each lecture with some learning objectives. These are the things that you should learn from watching this lecture. Our goal today is to first identify uses of concurrency. What is it good for? When do we use it? Identify sources of concurrency. Where do we have things happening at the same time? I want you to understand the scheduler's role in concurrency, meaning how it is the process scheduler, which decides what to run next, impact concurrency. I'd like you to be able to identify real-world examples of concurrency, how we work with multiple things happening in the real world, and also identify how you solve these problems in the real world. And finally, I'd like you to know the difference between benign uses of concurrency that won't cause any problems in your code from other kinds of concurrency that really need to be taken care of carefully. So let's start off by looking at concurrency in the real world. What is concurrency? It's really whenever you have multiple things happening at the same time that interact. Some examples are shared bathrooms, shared food in an apartment, and traffic lights or shared streets. So let's look at these in more detail. So here's a problem. You have a bathroom, and you would like to make sure that only one person goes at the same time. If two people go in at once, nobody likes that. So how do we deal with this in the real world? Well, the answer is we put a lock on the door, which somebody inside can lock when they go in, so nobody in the outside can get into it. The rule is if you go to the bathroom, the door's locked, you have to wait for it. So the point here is that we have something that's shared, which is the bathroom, and we have rules that express how we share it between people to make sure that bad things don't happen. For our next example, let's look at shared food in an apartment. Suppose you share an apartment with someone and you have a problem that you would like to make sure there's always fresh milk. How do you work this out with your apartment mates? Well, one way to do it is to have a note on the door that says whether we need to buy milk because you used up the milk and there's none left, and then another note to say you're actually buying milk. You need the first note to tell the other person there's no milk available and they need to get it. The second note is needed to let them know that you're buying milk so they won't go and buy milk themselves and leave you.
Okay. For this first example, so that's 216. For this first example, I think one of the things that comes out of all of this work, or with all of this instruction and all of this content about concurrency, is think of it as if you were in a bathroom that had many stalls, right? Because we're talking about running things at the same time. This is all of this stuff was making perfect sense to me, and now I'm realizing it's. Anyways, we'll keep going and we'll.
So the note here is, again, we have a shared resources, which is the milk in the apartment, and we have rules on how to share it, meaning we have rules that say notify somebody when milk is needed so that we will go get more milk, and notify somebody when you're buying milk so we don't end up with too much. Our third example is traffic lights and shared streets. Again, we have a problem that we have a shared resource, which is the intersection that cars in both directions want to go through. How do we make sure that cars don't collide? So again, we have rules and we have some state that help us figure this out. So we have a traffic light that tells us which direction cars are allowed to go. And the rule is don't enter the intersection if the light is red or yellow. And when the light changes to green in your direction, wait for all the cars in the intersection to exit. If you follow these rules, then it's safe for both directions through the intersection and there won't be any collisions. So what do we learn from this? Well, first of all, there's some properties of concurrent systems. The first thing is that there's multiple actors involved who can do things. In this case, it was the multiple people wanting to use the bathroom, or the multiple people living in the apartment, or the multiple cars that wanted to go into the intersection. Second, we have shared resources, the bathrooms, the food, and the street. Third, we need to have some rules that say how do we share these resources safely. One person at a time uses the bathroom, one person buys food, or only one direction uses the traffic light at a time. So how does this apply to computer systems? Well, we have multiple actors inside an operating system. These are processes. Multiple processes can run at the same time. Or we might have multiple threads within a single process that are running at the same time. So why might you have concurrency? Well, we've seen many of these before.
Good.
Suppose you have one process that is producing data and another process that's consuming it. Here we want to have the producer and the consumer running at the same time, but they both have to access the shared data for communication. A second reason is asynchronous I/O. For example, you might want to have a web server that can read data off disk and send it to the network. The network, the disk, and the web server are all actors. The shared resource we're worried about is the data moving between the network and the disk. Finally, we might have parallel programs where one thread will split the problem into 3 smaller problems worked on by different threads. Here, the shared data is the data for the program. The actors are the different threads. The reason to do this is that it makes the program run faster when you have multiple processes. Similarly, for asynchronous I/O, this can make things faster because we can access the disk and the net at the same time on different threads. Producer consumer, similarly, we can make go faster because we can be producing things while we're consuming them.
Right. Yeah. So I mean, the thing is, I have a lot of videos on this, and so at some point, just through the repetition and the stopping to talk about it, I hope that it comes together. But the idea of concurrency and parallelism and multi-threading is really all around taking massive problems, breaking them up into smaller pieces, and running them at the same time, then reassembling. Anyways, so, it might overwhelm if this is your first time through it, and otherwise, like, just keep going, hang on. Might be a white knuckle ride for us, but like, through repetition, we're gonna try and get it.
So the properties we have for concurrent computer systems are very similar to the concurrent systems we had in the real world. We have multiple actors, in this case multiple threads. We have shared resources, which can be memory, heap variables or global variables, or devices such as the network or the disk. So one thing to worry about is, well, doesn't the scheduler handle this for this? Because the scheduler is responsible for scheduling threads and processes. It is possible the scheduler will help you out and make things run in the right order. However, there's no guarantee this happens. In fact, the only guarantee the scheduler really makes is there will be no starvation, that every thread or process will eventually run. Schedulers generally make no guarantee of fairness, meaning that process A and process B will run the same amount of time, or timeliness, that process A and B will get to run in some finite bounded amount of time, such as 1 second. One way to think about this is that when reasoning about concurrency, we really try to think about the scheduler as an adversary. It will intentionally switch between processes at the worst possible time to cause the worst thing to happen. For example, suppose we have the code here shown here. Process A tries to count up to 10 and will print A1 when it gets to 10. Process B will try to count to -10 and will print B1 if it gets to -10. What could happen here? Well, it's possible if you have a uniprocessor that process A, if it starts first, will run and win right away, or process B, if it starts, will run and win right away. If A and B are running at the same time, then it's possible that they'll sit there forever, and neither of them will ever win because they will take turns incrementing and decrementing I. What this means is we really can't count on the scheduler to help us out in these problems. So one thing to know is, when do we not have to worry about concurrency? When do we not have to worry about multiple threads running at the same time? The first case is when there's no shared data or communication. Suppose we have 3 threads operating on...
So to be clear in this last example right here, they're both operating on the same variable, right? And so anyway, so it's like if you've got these 2 things operating on the same variable, one of them's trying to count up, and it might go 1, 2, 3, and it would maybe get, and then the scheduler will say, oh, we got to run this other one in parallel, and so then it'll go 3, 2, 1, -1, and then it just sort of bounces. In theory, it sort of bounces back and forth until one of them. What do you think about that, John? This is threading, and so thread. This could happen within. Yeah. Right. So this could happen in a JavaScript with asynchronous things, right? And so this is what we would call in that case almost like saying it's a race condition, but this would come down to something like a multi-core processor system where, or actually, let's talk about a computer where you have a single processor, and so a single CPU, a single core, and so in order for 2 programs to run at the same time on a single core, you have to have a scheduler that says this one is allowed to run for about 15 clock pulses, and then this one's allowed to run for 15 clock pulses. And the scheduler won't tell you when each one is going to run it. You just have to trust it. So it's like, process A runs for a handful of clock pulses, and then process B runs for a handful of clock pulses. And like, that's what's going on, is if each of these is running in its own thread, but not at the same time, it switches back and forth, and that's what's going on. Now I'm going to scroll up and make sure I read everything here. And JavaScript is just, so we're going through all of this stuff about multi-threading, but that's for non-JavaScript languages, because JavaScript is what they call single-threaded. And so understanding all of this is like, well, I'm going to be working in JavaScript. We've got to throw it all away. And so JavaScript is really going to change how we learn and teach this stuff because it's so different from classic multi-threading. Yes. Single-threaded monster, async instead of threads, async await and promises. Yes. Yeah. And right. And so this, yeah, good. So that's right. So it's like we're going to learn all of this multi-threading stuff and then we're going to throw it away because JavaScript, right? But it's like, we want to know this. And, spoilers, but one of the next guys we're about to talk to is really cool because he explains all of this stuff using assembly language. And so we're going to be talking about the way this stuff goes with like push and pop on the and he's going to talk about what's happening on the actual level of the silicon. And so I'm really I didn't want to start with him, but that's really cool. Yeah, and so this is a lot of the stuff when you search in concurrency is about Java, is about concurrency and how it works in Java. Although C++ and C# and everybody else has threads that I know of except for JavaScript. Anyways,
to help us out in these problems.
Going.
So one thing to know is when do we not have to worry about concurrency? When do we not have to worry about multiple threads running at the same time? The first case is when there's no shared data or communication. Suppose we have 3 threads operating on 3 different data structures, perhaps 3 different arrays. In this case, they're all working on separate data. There's no sharing and no communication, so there's nothing to worry about the concurrency. The second time we don't have to worry about it is when we have read-only data, meaning that it's constant. So even though we have shared data, in this example a hash table, the threads are only reading it, so there's nothing that can go wrong. There's no chance that one thread will modify the data and some other one will see the wrong value because the data is constant. Some examples of data that is not shared are local variables in your thread stack. These are private to the thread and generally not shared. An example of read-only constant data are global constants that you compile into your code. So what about risky concurrency? When do we have to worry about things? Well, if we have multiple threads accessing a shared variable without any kind of rules to access it, we have a problem. This is like having a shared bathroom with no lock on the door that people can walk in at any time. The second thing we worry about is when at least one thread modifies the resource. So in our hash table example, if one of our threads is inserting into the hash table while the other ones are looking up, it's possible the threads might see the hash table in the middle of an insert and see invalid pointer or a null pointer and crash. We call this a race condition, which is when we have 2 threads that are accessing the same data without any kind of rules for access. And we'll talk about this in the next lecture. So a standard example of where concurrency matters is in a bank account. Suppose you have a bank server that is managing an account balance. It has one method, a withdraw method that takes an account number or account object and an amount of money to withdraw. And we have 2 people trying to call it at the same time, shown here in pink and green. Both times the code gets called, it does the same thing. It reads the balance from the account, it subtracts the amount of money withdrawn from the balance, and then updates the account's balance with the new value and returns the current balance. So this seems like it's fine if 2 people withdraw at the same time, but let's look at what can go wrong. Suppose we start out with $100. Now remember, these 2 functions are being called by 2 different users, meaning logically in a computer system they'll run on 2 different threads. The scheduler, as I said, can interleave these 2 threads in any way we want. So suppose we have the interleaving here where time is starting at the top and going down. So we start off with the balance at $100. The first thread to execute is the pink thread, and it executes up to the point where it calculates the new balance at $90. If we now switch and start running the green thread, it will try to be removing $20, and it'll execute down to the point where it sets the balance to be $80. The pink threads can start running again at this point, and it will save the balance as $90 and return. When the green thread starts up, it will save the value of the balance as $80 and then return. The problem here is at the end of this, the account balance is left at $80, even though $30 were removed from the bank account, and it began with a balance of $100. The problem here is that we have a race condition. Both threads are modifying shared state, which is the bank account balance, with no rules about how they should be synchronized. So remembering why this happens, we need to look at what is shared. As I said, concurrency is benign when we have things that are not shared. Local variables are not shared because they refer to the thread stacked. What this means is that you should never store a pointer to a local variable in a global structure, or else that thread stack may become shared. Global variables are, however, shared because they're stored in the data segment that's accessible to all threads through the name of the global variable. Heap variables may or may not be shared. When heap variables are first initialized through the malloc call, only one thread has access to that data. However, if another thread can get a pointer to it, for example, you store a pointer in a global variable, or you store a pointer in another variable that is already shared, then that data becomes shared. This means that heap data variables are private if only local variables can point to it. So how can we manage concurrency? Well, there's a couple of techniques that computer scientists have developed over the past 50 years for this problem. The first is a set of synchronization mechanisms that allow programmers to write rules on how to manage concurrency, just like the lock on the bathroom door. One of these is atomicity. This is basically make sure that while one thread is modifying data, no other threads can change that data. This is similar to when you're in the bathroom, you make sure nobody else can come in the bathroom. The other major technique is conditional synchronization. This allows code in different threads to run in the correct order. Suppose, for example, you want to make sure that code that withdraws from a bank account waits until there's enough money in the account to withdraw. Conditional synchronization would allow one thread to wait until the bank balance is high enough before the withdraw runs. This is the end of the first lecture in concurrency. Please take the quiz.
There we go. So, I mean, yeah, it's I don't think that any of these guys that I've watched or checked out actually has any talk about async or await. Yeah, fake. Can you fake? Also, hi Pebs, super super happy to see you. Thank you for showing up. I don't know. You haven't met John. John is here for the first time, but he's had an interview. So actually, you watched his interview and pointed out the audio problem that I had, which I have fixed. So yeah, the JavaScript, it changes things, but now we still have race conditions, right? So it's like, but we have race conditions when we have to worry about network return times and everything. So it's like, you know, we still have JavaScript runs the world. Yeah. So what I'm trying to see, so this guy computer file is really good, and I'm trying to decide which one is exactly the right one to watch next. So multi-threading, this one, or multiple processor systems. I think I'm going to go here because he gives another example of what's going on, but he explains it and he codes it, and we can, anyways, he's
if you've got multiple processors, either that's multiple cores, virtual cores in a hyperthreaded processor, or actually a multi-core processor, you want to run your algorithm or on multiple CPU instances. So you need to split it up, and the operating system needs to find some way of controlling all those different instances. Actually, it can still be beneficial on a single CPU system, because there might be times where part of your program is waiting for, say, network inputs.
I should say that this is a pre-roll bumper. It actually goes. This is a click. Anyways, this is it is better structured than this. I should have jumped ahead. So, oops.
So the operating system will then schedule in another thread of execution to do something. So let's start by thinking about what the operating system sees when it's running a program. And this is what's called a process. And that's got a series of instructions that it's going to be executing. This is the program. This is actually not part of the operating system, it's the program, but it needs to know where inside the program that is. So it's that instruction, say. But there's also lots of other information that the operating system needs to keep track for a process. So things like list of open files, configuration of memory, and so on, if you've got virtual memory involved, or paging. There's just various things that the operating system needs to keep track. Each of them has got a unique ID, and you can then run multiple processes at the same time. So one way you could break your program up into multiple chunks is to actually have multiple processes running. And for a while, people did this. They sort of would use the command, a function in Unix, for example, called fork, and it would split the program in two. One half which would run off as it was, the other would have a new process identifier, and the operating system would copy that block and create a new list of what memory it uses, a new list of the files it had open. Now these would point back to the same files, the same blocks, memory allocations and things, so that if you changed one memory location, it updated on the other side and things. If you changed a file,
part of the reason I liked him so much was because he has all of these computers, and you think, who the heck is this weirdo? And, well, I mean, not really, like, because you really like him instantly if you are also a bit of a weirdo. But what's really funny is I think it's in the next video. He actually uses some of them, and you start to see the value of a high-end computer scientist having super old computers in his lab where he just runs things. So, he's got Ataris, he's got, like, anyways, he's so good. I really enjoyed this guy.
To a different part of a file, for example, it would update in the others. But to they would be separate processes, and they'd have to have all the storage required to do that. And that worked, but if you're just breaking your program up so you can run your task on multiple CPUs, most of them are going to have the same list of files, the same memory configuration, the same everything else that the operating system needs to keep track of. The only thing that's going to be different is where it is in the program, what bit of code it's running from what part. And so the idea that came along was, okay, well, let's have something lighter weight than a process. And they called it a thread because you've got your thread of execution through the instructions. And what we'll have is that each process will have at least one thread of execution, but could have many. So you have multiple threads of execution in your program. So your program's running one thread which it starts off with. That will then create another thread which does something, and then another thread perhaps and so on can do different parts. They may last for the whole length of the program. They may only last for a short part while that task's being completed and so on. You may have multiple ones that get jobs from different things and so on. How you structure your program doesn't matter. But from the operating system's point of view, it's now scheduling different threads onto the different cores, whether that's 1, 2, 4, however many you've got in your system. So the idea behind multi-threading is a sort of lightweight way of saying to the operating system, these are the different things that I want running on my computer, whether that's all as part of one program or multiple threads through multiple programs. And the operating system is choosing which one of them actually gets CPU times on any of the CPU cores, physical or virtual, that they have available.
Right, so that's the scheduler that we were talking about previously. So the scheduler is the operating system. The processes the processes or threads are, you might have multiple programs running at the same time, a finger for each program, or you might have a single program that has multiple threads inside it, that has multiple processes. But the other thing that he's saying there, and that it's important to call out, is some of these programs are accessing the same system resources at the same time, right? And so we can have two or three different processes that are trying to access the same physical file on disk. And so that's one of the reasons why, for example, if you try, let's say you've got Visual Studio Code open and you open a file and then you go somewhere else in your operating system and you try and move the file and you get the operating system warning, this file is locked, cannot access the file, it's being used by another process. Those are the sorts of things that we're talking about. I'll let him keep going, but it's, I hope, nice to sort of take a break and summarize and restate to see what we're actually talking about in each of these conditions.
Now that introduces, if you're writing one program that you've split into multiple threads, that introduces some interesting issues, because you can get to the point where your programs can no longer do the task that you expect them to do. A program which was just one single stream of instructions executing one after the other, and so you knew the order they'd execute into, to multiple threads of instruction that are executing, sometimes in parallel, sometimes one after the other, but you no longer have any control over the order that would happen, because the operating system might put two of the threads on at the same time, or it might let one thread run and then put the other thread on after the other and then go back, and you can't control where it switched from one to the other. I can show you this with an interesting program on my laptop. So what I've got here is I'm going to write a program that adds up all the numbers from 1 to 1 million. But I'm going to do that in two threads. So I've written two threads here. I'm going to create two threads. The first one is this routine here, which is called the helpfully thread function. We've got a variable a, which we're going to initialize to be 0. And I've declared this as a volatile variable, just to tell the C compiler that it will change when it's running, because otherwise you'd have even more problems. So I split it in two. So the first one is adding up the first 500,000. The second one, exactly the same, except it's adding up the second 500,000. So what it's doing is it's adding up from 500,000 to 1 million, and they're adding them to the same variable. So we've got instruction is going to fetch one, add it on the next one and write it back, and then the other one's going to fetch it, add on a value and write it back, and so on. So then we then run our program, where we create both threads, and then we wait for them to complete, which is what this pthread join is doing, and then we print out the number that we've got. So if you would like to add up all the numbers between 1 and 1 million while I run the program, then we'll see what result we get.
500 billion?
So let's just compile this up not made any mistakes in the program, so we compile this up, and let's just run this program. And it's given me the answer 286689748260. If I run it again, I now get the answer 3339638266726. If I run it again, I get the answer 3268704095221. If I run it again, I get 2430750154992, which sounds like a phone number.
Will this all converge on the right answer, or will it average out, or is this just one of those completely...
Well, if you think about it, it should always be the same. You're adding up all the numbers between 1 and 1,000,000. You should always get the same answer. It shouldn't be converging on something. It should always be producing the same answer. So something very, very odd is going on my computer. Something very, very bizarre is going on. We could write the program. In fact, let's just write the program normally. Let's comment out all this, and we'll just write a very quick program that adds up all the values from 1 to 1,000,000. So while I is less than or equal to 1 precise. So we've made it a single-threaded program now. It's just going to run on one thread. And if we do that, we recompile it, we now get the same value each time, 500 and whatever that is.
So now we've gone single-threaded, we're getting the right answer.
And we're getting the same answer each time. So what's going on here? Well, you need to think about what's happening in this program. So let's just put it back to where it was. If we look at this instruction here, a equals a plus I, then what we're telling this program to do is to fetch the value of a, whatever that is, then add on the value of I to it, and then store the result back in A. Now, if I just put that to one side and find my paper, which is over here with my pens, if we were to write that in machine code, and I'll use the ARM chip to do that because it just makes things slightly easier to see what's going on, we would have, this is thread 1, so we'll call this T1. We're going to say that this is going to be an LDR instruction to load a value from memory. So we're going to load into a register. Let's use R0, the value of A. We're then going to add on to R0 the value of R1, which is a register containing our loop counter. That's the same as I on there. And then we're going to store the value of R0 back in A. So that one C instruction becomes 3 machine code instructions. So the way that the program is executing in...
I just want to stop. How smart do you feel when you're learning about multi-threading and like there's assembly code coming up on the screen? You know, like you feel so smart, like sitting around pretending like you know what's really going on there, and he's yeah, I really enjoyed this one, so I'm glad you're liking it too, John. That's
one thread. It's loading the value from memory, and it's making a local copy of it, and then it adds a value onto it, updates its local copy, and stores it back into the actual location. And that thread keeps doing that into a loop. So it loads it, adds something onto it, and stores it back. Loads it, adds something onto it, stores it back. Now, if we've got a multi-threaded system, which is what we had there, we also have another Steve. Hi, Steve. Hi, Steve. And in that case, I'm going to be here loading the value, adding a value onto it, storing it back. And I'm going to be here loading a value, adding something onto it, and storing it back. So I'm loading a value, adding something onto it. I'm loading a value, loading a value, adding something onto it, storing it back, storing it back. And what's just happened, because other Steve had added something else onto it while I'd loaded on, when I store mine back, his update doesn't get changed. It gets lost. Well, that wasn't nice. So if we look at what's happening on the paper, it's loading the value in, it's adding the value onto it, and then it's storing it back. But of course, we've got multiple systems. And so at some point, this program is going to start executing the same code. So let's cross this instruction out for now. We'll put it back in a bit later on. And assume that at this point, we load the value into the other thread, into R0 in there. And then we do the add-on in the same way, ... And then we do the store back here of R0 into A, and we've got 1A up here that we're accessing. And then this store actually happens after this store here. So what happens here is that these both end up getting the same value of A. This adds its value on in its local register. This adds its value on in its local register. This stores it back. Then this stores it back. And of course, because this has just stored it back here, it's overwritten the value that was stored there. So the value that was added on here gets lost. So what we need to do is find a way to synchronize these two things so that as soon as this has loaded the value in and is going to add something onto it, it stops this one from doing it. And so there's a couple of ways we can do that. The easiest way is that we have something that both Steves or both CPUs have to access. And so we could have a token. Let's use a floppy disk, Microsoft Office Professional, 1995. And what we're going to say is that I can only access and update variable A if I have the token. So let's bring back friendly Steve. So we've now got a token, and what we're going to say is that unless I've got the token, I cannot access the variable A. So I'm going to execute those three instructions whenever I've got the token. So I'm going to load a value in, add something onto it, and store it back. And then I'm going to hand the token to Steve. Now I've got the token, so I can load a value in, add the value on my register into it, and store it back and hand the token. And now I've got the token again. I can load something into my register, add something onto it, throw it back, and pass the token on. And I've got it, so I can load the value in, add the value from my register, store it back, and pass the token on. And because I've got the token again, I can do the same again. But because only one of us can hold the token at any one time, it means that only A can get updated when we've got the token. And so we never lose that right.
Yeah, exactly. Like that one doesn't seem faster. So what are you getting out of it? At least in theory, we should understand what the concept of thread safety means at this time. But he does, I hope, in this one, get to how do we solve for the fact that we've just ruined our problem with speed. So
because we're saying that unless you've got the token, you can't access that variable. That's great. So if we turn back to the laptop, we can see how we can implement that in our program. We're going to use the same idea. We're going to have something that we need to have before we can run that code. In this case, we're going to have what's called a mutex, an area of mutual exclusion, that we need to lock before we can run the code after it. And then when we've finished, we unlock that. And so if it's locked and we try and acquire it, our program will pause until it is able to lock it. So what I'm going to do is I've created the variable for it here, and I've also initialized it down here, so it's all set up, ready to go. So before I add onto A the value of the instructions, I'm going to lock that mutex, like so. And then afterwards, if I could type, I'm going to unlock that mutex, like so. And I need to do the same in the other thread as well. So I'm going to lock the mutex. And then I'm going to unlock it afterwards. So if I compile this version up, we've still got two threads. We're still getting them to add up the things as we go through it. And then at the end, we're going to print the result. And it should, this time, give us the right answer. So let's run it. And it gives us the right answer. We now split the problem in two. It's running on two CPUs. And because we're locking that variable so we can only access it in one thread or the other, just as we did with the two Steves, then we can get the right result. And it produces the same result every time. Now the downside to this is that locking the thread each time slows the running of the program down. But we can be clever. If we think about addition, if we add 6 numbers together, that's the same as adding 3 numbers together, then adding 3 numbers together and adding the results of both together. And we can do the same thing here. So we can take this mutex and move it outside of our main loop. And instead of adding on the value of I each time, we have a local variable, we'll call it local A, which we add everything onto. So we say local A equals local A plus I. So inside our thread, we're just going around adding all the values on as we did before, which didn't work. But because we're putting it in a local variable that's local to that thread and this function, it's not going to be a problem because only this function can access it. We'll do the same in the other thread, and then we'll do the same thing outside it. And the advantage of doing this is that we now only have to acquire that lock once in each thread. Rather than having to acquire it for every single addition, we only have to acquire it once. So if we time the program before...
Now, it is, but remember what the other things we talk about in that sort of code interview stuff. Remember your time and space complexity. by adding 2 new variables, what have you done to your space complexity? So you've split the problem in 2, so you've improved your running time, but you have increased the amount of memory that your program needs to run. And like, obviously this is a tiny case, a tiny example, but it's the broader picture that we want to think about when we're dealing with actually writing code. So it's like, more variables. Anyways, so that's...
And I should say at this point, the program may be running so fast that we won't be able to get an accurate time on it. We can try it anyway. So we use the time command to time it. We see it takes about 0.82 seconds. Let's just run it again. 0.71, 0.71. We seem to have standardized around that sort of thing, so about 0.7. So let's compile up our faster version now. Not made any mistakes, and we'll time it again. Well, let's see it produces the right value. We'll time it as well. And it's taking around the same time. Like it's dropping a bit. And it doesn't really make any difference in time. I think that's just because of how fast the computers are that we're dealing with. But with a bigger program doing more calculations, reducing the number of times we acquire that lock would actually make the system run faster. So multi-threading is the idea of breaking our program up into multiple threads of execution that run for different lengths of time, but we have to be careful that we do things in the right order and we avoid having multiple threads accessing the same variable at the same time, particularly if they're writing. If they're just reading from it, it doesn't matter, or if one's writing and several are reading from it, and it doesn't matter if they perhaps get an older value at a time, then it works fine, and so on.
That same A1, so that he...
There we go. Yeah, he fully YOLOs his stuff. I don't know. I mean, he clearly did edit it. Like, there were 2 Steves, so he did some spots that were good. Now, this is more on the same topic. The first part, he goes around the room and he sort of looks at all of the computers in the room, and it's really fun. But it is not key to the topic at hand. And was it here? Oh no, maybe that's the right time. This must be where it really starts. Okay. But yeah, so I think from the previous video, the question is sort of what did we get from his breakdown of multi-threading? We kind of learned... We kind of learned where thread safety comes in. We kind of learned about one of the advantages for doing... Why would we do threading? None of this is valid for JavaScript, and I did look, but I didn't find anything that really talked about the threading in JavaScript. Nothing that was quite good enough. And so I'm going to try again for next week to try and find something that really illustrates the big fundamental difference in JavaScript, because I think it's important to know. But here in this one, the talking about having multiple processors in your system is a slightly different way to look at this whole threading issue. But, these are the things we want to come away with. Understanding what concurrency is, breaking it out into multiple processes, and understanding thread safety and where things can go wrong with thread safety. And now, what's this guy's name? I've liked him. Yeah, here it is. Dr. Steve Bagley. He's pretty great. He's pretty great.
GPU is generally being used for a specific task, things, whether that's graphics processing or Bitcoin mining or whatever it is you want to do on it, depending on whether you're wanting to make money or lose money. And I can let you work out which one of that is going to do which.
Surely we're using multiple cores purely because we ran out of horsepower on single cores.
So why are we using multiple cores? Good question. So the thing is, you want to make the problem run as fast as possible, and you've got 2 ways to do that. You can either make the computer run faster, for example, speak faster, you get more words per second and so on, and you get it going, and you do computer more doing more and 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 more faster and faster and faster and faster and faster. The problem with that is you get to a point where you can't actually push the computer faster. There's a thing called the power wall. That's the point where you can no longer dissipate the heat away from the CPU. We actually hit that quite a while ago, but you were able to reduce the voltages used on the chips, which meant that you could get a bit more and then do it again. But apparently we're getting to the point now where the voltages are so difference between the logic 0 and the logic 1 is so low that actually you take it any lower, you'd get leakage between the transistors on the chip itself, and so it's not possible. So you can push the speed in one way. The other way you can make the program run faster is to split it up into multiple chunks and do them all at the same time. So one way, for example, to make sandwiches faster is that you butter the bread faster, you put the filling in faster, you put the bread faster. The other person is you get two people doing it, and then it takes them the same amount of time to make one sandwich, but you've got two people doing it, so they make twice as many sandwiches each time they make a sandwich. Same with the computer. We could either make the computer processor faster, or we can have multiple cores, each working on part of the problem at the same speed, and then we can have them produce the result faster. To do that, we need to be able to break the problem down into multiple chunks and execute each of those chunks separately, which is one problem. You need to work out, can you break the problem down? Can be quite simple. If you're, say, processing an image, you want to, say, make it 50% the brightness, then you can process the top half, process the bottom half separately, do them at the same time. You halve the time it takes to process the whole image. Other tasks are harder to break down because you need to work out how you want to break down the algorithm to run over different things. Asymmetric and symmetric multiprocessing systems aren't really competing for each other. It's not, this is how we used to do it, this is how we do it now. You would find that there were multiprocessor systems back in the 80s and 90s. Parallel processing was a big thing in the late 80s, early 90s. People were looking at parallel architectures for doing all sorts of things. In fact, one of the things which describes how parallel systems work, Flynn's taxonomy, was created in 1966. So the ideas have been around for a while. I think it's more that for a lot of things, when you've got a task that you want to do in different things, symmetric multiprocessing makes sense. For other things, having an asymmetric system, whether that's your DSP, your I/O processor, a GPU, a TensorFlow type thing, and so on, makes more sense like that. So how you design a multiprocessor system is very much based on what you're wanting to do. What are you trying to do with it? I mean, Flynn's taxonomy is an interesting thing because you then get some really weird processor types coming up. So you can either have a system which has got a single instruction stream or multiple instruction streams and a single data stream, or you can have multiple data streams. So you'd end up with a single instruction stream, single data system, or multiple instruction stream, single data system, single instruction stream, multiple data system, or multiple instruction stream, multiple data system. So a modern multi-core CPU will actually at times behave like a single instruction stream system, at times behave like a SIMD, single instruction stream.
I'm gonna look that up in a different window there, see if we can. I think it is that chart that we're looking at right now. So Flynn's taxonomy being the. I've certainly seen this one here. The
data system or multiple.
I've seen SIMD.
Multiple data systems.
In
so
literature
modern
before,
multi-core CPU will actually at times behave like a single instruction stream system. At times behave like a SIMD, single instruction stream, multiple data stream system, and at times behave like a multiple instruction stream, multiple data system, and we end up with these all being used at different times. The easiest way, think about it as a single instruction stream, single data stream processor. That's the sort of classic model of a processor. You've got a set of instructions that your program's executing, and you could think of these flowing through the CPU, one after the other, okay, with the occasional branches, like water flowing through a stream. If you look at one point, the water flows through at that point, that's what the instructions are doing, they're flowing through the CPU. And each of those instructions is probably going to be loading a value from memory or doing some processing on the value that's come from memory and then putting it back out to memory. So if it's, say, I don't know, let's say it's rendering 3D graphics, you're going to be doing lots of matrix multiplications and things on that you can then pull the data in, do the calculations and write out the new points and so on. Now what Intel did around late 90s, they introduced what's called the multimedia extensions, MMX, and that was followed by SSE, SSE2, AMD's 3D Now and various other things that do different things, which basically add what are called single instruction, multiple data instructions. So these instructions are still a single stream of instructions that say we're going to add something, we're going to multiply something, but rather than just acting on one piece of data at a time, they can act on multiple pieces of data. And if you think back to that 3D graphics, you, for example, will have your X, Y, Z coordinates for, say, your shape, and you normally actually store that as 4 coordinates because you have the X, Y, and Z, and then you have a 1 in the vector because it makes the math slightly simpler. And so you might actually then call that, need to multiply that by a matrix. And with a SIMD type instruction, you can read those 4 values and read the 4 values from one column of your matrix and multiply them all together, which is 4 separate operations. But if you can use an SIMD instruction, you can do that in one operation working on 4 separate bits of data. So it multiplies the first pair together, the second pair together, the third pair together, and the 4 pair together, all in one instruction. So they added extra bits.
So for the for those of us, myself included, who have not done computer science in school, the matrix multiplication is like central to almost everything on the computer. Like I've been doing the Coursera course on machine learning, and everything is how do we multiply a matrix. And when you're working in 3D and computer graphics for video games or whatever, it's all matrix transformations. And so when he's talking about using special computer chips to do matrix multiplication, that's a really big deal. That's a really big deal. I mean, Pebs and John probably know that already, but that's for the rest of us. That's a big deal.
New ALUs, new designs for doing things that enable them to have these instructions. If your data is structured, the data you're processing is such that you can take advantage of that, you can get some significant speed boosts, because rather than doing 4 instructions, you have to do 1. But you're taking advantage of what's called data level parallelism. The processing you want to do enables you to do those instructions on multiple data options at the same time, and you get some sort of speed up. It works for some tasks, 3D graphics, for example. For other tasks, it's less useful, and so you don't benefit from them. But the other thing our CPUs can do is that they have multiple cores, and modern CPUs, the Intel i7, AMDs, and so on, are all multiple instruction, multiple data things. So they have separate cores, each of which are running their own stream of instructions, so they're on different bits of the program or different programs altogether, processing different bits of data, still a single stream per processor instance, but unless it's an SIMD bit, and so you can have multiple data streams. And so you have them running all of these things. And that is pretty much what people think of as parallel processing, multiprocessing and things, is you've got multiple CPU cores running their own programs, processing their own set of data. So we can build up different things, and they've been around for years. As we said, various different types, symmetric, asymmetric. The different ones of Flynn's taxonomy have been around for a while.
I think you're probably right, John, because if you think about the first, what was it? It was like the 3D effects, or the Voodoo 3D graphics cards were the first Voodoo 3D effects, right? And that came out specifically around, it was around the time of Quake, or maybe late Doom or something. Quake was probably the first one I recall. And all of that must have just been a natural progression. You say, well, listen, if Intel is doing MMX, they're doing a small area of the chip where we can do slightly faster multimedia or matrix transforms. Why not have a whole chip for it? And that's where we added our Voodoo 3D effects, and then progress. And today we're at the RTX 3080 real-time ray tracing, which is boggling to think that it's happened in our lifetimes. So
that leaves us with this weird one in the top right corner of the diagram, which is the multiple instruction stream. So you've got multiple streams of instructions acting on a single data stream. Yeah, they're weird. Not many of them exist these days. I think the most prominent example that I've heard of, I've never actually had to program it, more's the pity, is the Space Shuttle Guidance Computer.
3, 2, 1. liftoff of Space
Apparently the Space Shuttle Guidance Computer uses a multiple instruction stream, single data stream machine. And perhaps one of the reasons you might want to do that is that it enables you to, say, do multiple calculations and then get some sort of fault tolerance perhaps out of it.
Touchdown.
So you can build parallel processing in different ways. But the one that we're perhaps most familiar with is that we've got multiple CPUs in our computer, whether they're physical chips, physical cores, as they perhaps used to be, or they're multiple cores on the same piece of silicon. And if we're doing that, we need to make those multiple processors do useful things. So the simplest thing we could do is get the operating system to schedule multiple programs, multiple processes across each of the different CPUs. But that enables us to run multiple programs very good, but it doesn't really give us any speed up in terms of running a single program to solve a single task. And to do that, we actually need to break the problem down into multiple chunks and execute a chunk of each of that problem on each of the different processes we've got available to us, whether that's 2, 4, 6, 8, 32, however many we've actually got to deal with. So we need to break our problem down into multiple, what are often referred to as threads of execution, and run them on different CPU cores.
Uses that same A1.
That that one reminds me, I have not actually, I had not planned on showing this video, and I'm not going to do it because I don't know which one it is, and so I don't want to waste anybody's time. But there was, I think that it's a Linus Tech Tips video, and I will track it down and find it at some point, and maybe I'll show it next week. But he goes into detail about how on the silicon level, how the M1 is different than all of the AMDs and Intels and everything out there, and it's a really exciting picture of, you know, the M2. It's a really exciting picture of how things are progressing and how they're doing things differently. So we might be at the next major paradigm shift on the silicon level coming from Apple. And what did we just see? I think we just saw NVIDIA bought ARM, and ARM is known for making mobile chips, which is closer to the style that Apple builds their chips in. And so there's interesting stuff happening in the chip space, and also who knows what's gonna happen. Like, it's just anyways. So how are we feeling about thread safety? I think talked about specific low-level yeah, I think so. I think that that guy, I found him last, but I think he's by far my favorite. Yeah, and the bathrooms. Yeah, I found that, as I say, I found that one second, because I found simple multi-threading, and it seemed okay, and then it's like, what I failed to do was go back and edit out the ones that were not good anymore based on how good the other ones I found were. I also don't know that we need... Let me open these up and see, just to remind myself. This guy, he seems nice. Gary explains he was very nice, but I think we've covered this at a very good level. And this one, no, this one is going to be boring, so I think we'll skip this. I think we kind of understand thread safety based on what Dr. Bagley was saying. Dr. Bagley was just saying, listen, you've got a thread problem if two processes are trying to write to the same piece of data and it overwrites itself. That's the problem. So thread safety is making sure that doesn't happen. If you feel you need more, the resources are here, the repo's online, you can load the things and watch them yourself, and if you have feedback, you can tell me that I was a fool to leave it out. But I think I want to quickly look at some of these, the types of concurrency questions you might see if you're going for an interview. And then this one is, I really liked this one. So let's look at some of the questions, and this one is a long one, but I think it's really good, and there are pictures of cats, and they're really cute. So, so some of the questions you might ask, what's the difference between a process and a thread? Yeah. So, I mean, that's worth watching for the cats alone, I think. I think she drew pictures of all of the cats, I think, for her presentation, and they're really, really cute illustrations, and they're funny and heartwarming. And so, oh, you open this wide enough and you get other stuff. Okay. What are the benefits of multi-threaded programming? I think if we walked away from today, you could probably answer that. What is the difference between user thread and daemon thread? I don't know. Don't ask me in an interview. I could sort of probably BS on that one, but how do we skip it? What are the different states in the life cycle of thread? I don't know. Anyways, let's instead let's instead say that these resources are here, and you can, if you are going for an interview, you can start. And these are the types of things. You have a thread T1, T2, and T3. How do you ensure that thread T2 is run after T1 and T3 after T2? There you go. So if there's a user thread running through the Java program, the Java program will keep running even if main exits. Oh, so really? So exiting a program doesn't end all of the threads? That's scary, isn't it? What are the difference between wait and sleep? If you have an interview, there are resources for questions there. So like the garbage car, right? Okay, yes, yeah, okay. Okay. So a daemon thread would be spawned by your main process would spawn a daemon thread, and it will run regardless of whether your program is still running. That makes sense. That's really useful. Oh man, we should go through all of these now, John. You can answer them for us. Oh, that's good. How do we? Anyways, so what's serendipity to have a? Oh, Glenn. Oh, that's okay. It's so nice to see you, Glenn. I don't know if you see. We have John Kugelman has showed up today. Which is great. John has an interview on the channel, and I'm really, really happy he's come along. He's already teaching us stuff, and I hope you're well. I hope you're doing well. Yeah, it's really good to see you. Thank you for coming. Okay, so I'm really excited so Glenn, to get you up to speed, and you're welcome to watch it back as you go and see it. But we've in fact, I would recommend watching it back instead of going through these on your own, because some of them are terrible. But what we're talking about today in the first half, we've just sort of finished, is multi-threading and multiprocessor systems, and sort of working on how do things work on the level of the silicon or on the level of the chip. And we're just about to talk about about distributed systems, which is sort of like designing multi-threaded code, but on a larger scale across multiple systems, like multiple computers running at the same time across network connections, is what we're effectively talking about in a lot of ways is parallel computers or parallel processing on multiple computers at the same time. And that would probably make a lot more sense to you if you were here for the bit where we talked about multi-threading, multitasking, multiprocessing. But it's okay. This one is also probably viable as a standalone piece. And there are pictures of cats. So highly recommended. So what's really fun about this, I didn't know this when we started. She is actually a Toronto, Denise Yu is actually a Toronto developer at GitHub, which I didn't know until after I got to a certain point where I laughed so hard that I had to look her up on Twitter and send her a message telling her how great I think she is. And I looked at her bio and she's in Toronto. And so this is the story of why distributed systems are hard. Anyways, really good. I really like this. I love her illustrations. So let's begin.
Hi, thanks so much for having me. My name's Denise. This is the talk, Why Are Distributed Systems So Hard? If you're in this room by accident, you have a few more minutes to shuffle out and find the talk that you're meant to be seeing. But I actually want to start off, oh, we're actually a few minutes early. OK, that's right. I kind of run dangerously close to time anyway, so I'll just start. So I actually want to start by launching into a meta discussion, which is, why should we even bother learning about distributed computing in the year 2020? After all, we've all been using the cloud for a couple of years. Many of us are using open source orchestration tools like Kubernetes, for example, to manage our services for us. So the question remains, why worry about distributed systems theory and history in 2020 when we arguably have tools that might do our jobs better than we can? Because after all, we've known for a very, very long time how to run services. And isn't it the case that microservices are just smaller versions of services? So why pursue this type of architecture? Why pursue smaller, decomposed, decoupled services? I generally think that microservice architecture is motivated by a set of socio-technical goals. Among those goals are, perhaps you want to make your engineering team boundaries reflect the boundaries of your business domain. For example, if you work for an e-commerce company, rather than having all your front-end people over there and all your database administrators over here, you might instead build cross-functional integrated teams so that they all work on maybe some of them work on payments, maybe some of them work on search, and so on and so forth. But why do you want to do this? Well, if you can decouple your engineering.
Here, so that, I mean, that description right there was kind of like what we were just talking about, breaking these things up. You know, we break up the problem into smaller, more manageable, bite-sized pieces, and we run them at the same time. This is distributed. The distributed systems are like parallel processing for our application. It's just, you know,
engineering teams to look like your business boundaries. Maybe that means that you enable these teams to release and deploy more frequently and more independently. So the payments team might not be blocked on a feature that the search team has to merge into trunk before you ship, right? So continuous delivery, like higher frequency, more rapid deploys, all of these are good things. But why care about that? So I think like the pursuit of these goals supports the overarching goal that we ultimately want to improve the resiliency of critical systems that we need for our businesses to run. We want to protect these systems against catastrophic and show-stopping events. There's a lot of cat pictures in this deck. You've been warned. Because after all, like we've had microservices for a couple years now. After all, we know that if we're doing microservices, we can make a change to one microservice without having to change any others, right? OK, I'm just going to say that, take that as a yes. So, but I'm not going to stand here and preach to the converted. I'm not going to spend the rest of this talk rattling off a list of why microservices might be good, they might be useful in the right context. I'm going to presume that you're all here because you've at least heard of microservices before. Maybe you've used them. Maybe you're here because you have a healthy skepticism towards them. That's all fine. But the thing is that everybody, every team who runs microservices is now at the helm of a large distributed system. And how large, of course, is going to depend on the specifics of your business. So it's almost like a law in talks about microservices. You need to have one slide that shows somebody else's architecture. And this is my slide for that. So Monzo, it's a bank here, great company, fantastic people. I love them to death. Monzo hit 1,500 microservices at the end of last year. So this diagram shows all of their networking rules that govern how one service talks to all the other services in the system. But even if your architecture doesn't look like this yet, maybe, The truth is that the specific technologies that we use to manage and deploy and orchestrate these systems will come and go, and technology trends honestly are really fickle, just like my cat's dietary habits. But the fundamental principles for designing and operating services on top of distributed systems haven't changed that much in the last few decades. And understanding the fundamentals, taking some time to learn this stuff and to internalize it, is the best way to future-proof the systems that we're building today.
To be clear, that was the slide where I started laughing so hard that I had to go tell her how funny she was. I just, like, cats pushing glasses off of counters it's like crack to me.
And beyond that, I honestly think that just learning about distributed systems is really rewarding and it's really fun. So I hope that in the next 45 minutes and 35 seconds, if nothing else, you'll have fun. Like, I hope that you'll laugh at least once. I hope you'll enjoy the cat pictures. I found it really fun to learn about this stuff, and I hope you will too. So by way of introduction, my name's Denise. That's my Twitter. That's the wrong hashtag. It's actually QConLondon. So for accessibility reasons, I actually like to upload my slides 100% online before my talk starts. So you can access them right now if you go to deniseu.io/QCon. I grant you permission to take pictures, like live tweet, whatever it is that you want to do. If you want to use the highest resolution pictures, they are on there, not the ones you're snapping on your phone. So I'm a senior engineer at GitHub. I work on the community and safety team. Broadly, my team builds tools to make GitHub a more productive and safer place to build communities. I actually haven't started yet, so if you have specific questions about the team, I'll direct you to my future colleagues after. I'm based in Toronto. Go Leafs. Any other Canadians here? OK, there's like 4 of us. Yes. I'm actually not Canadian, I'm American. But I lived here for 5 years, so it's really fun to be back. And finally, when I'm not on stage rambling about cats and distributed systems, I spend my time making art about tech that bridges gaps in understanding. So feel free to check that out later if you want. A lot of the images in this talk are borrowed from a book that I'm co-authoring with my friend Steve Smith. So if you have any nephews or nieces or children in your life who are going to be writing enterprise software, please consider buying them my book.
Right?
So let's go on a journey together today. So broadly, we're going to cover a few big topic areas. We're going to talk about why distributed systems, why distributed computing is even a thing. We're going to do a recap. If you've studied distributed systems theory before, you might know that already. If not, don't worry, you'll know by the end. We're going to talk a lot about networks and partial failures, and then we're going to close out by talking about the human side of things. So socio-technical mitigations and how the human part of the system is the most adaptive, but possibly the most complex part of it. So history lesson time. How did this all happen? How do we get to where we are today? A long time ago, in a data center, not too far away. Maybe some of you know where, from your own experiences, where this data center is. All your business applications tended to be structured like this. So client-server architecture, you had multiple applications. They all read and write from the same database. That one database, like one database, was probably hosted on some machine that was in a server room with no windows in the basement of your building. And this worked for quite a long time. It worked because IT was just sort of a necessary evil. It was a cost center that we needed to support so that other people could go and do the real money-making operations. But this stopped being true at some point in the 90s, when computers stopped being this cost center for a lot of companies. I mean, there's that famous Mark Andreessen quote about how software is eating the world. But like, at some point in the 90s, computers actually started being business differentiators and competitive advantages, which meant that we had to start taking our IT functions a lot more seriously. And of course, the core value for a lot of businesses then, and for a lot of businesses today, is customer data.
Here's her. The Google SRE book was lacking in cats and dogs, so she went ahead and did that up for us. So, sorry.
So we as an industry have always needed better ways to read and write, to store and retrieve our customers' data. So as IT became a differentiator, the way that we stored and retrieved our data, of course, evolved. So today, it's usually not, like, I don't want to say it doesn't work for anybody, but for most companies, it's not sufficient to just have your one massive database on one server in your basement anymore. Why, though? So one sort of pusher here was that data-driven business analysis is increasingly important, and business analysts and product managers want to run expensive SQL queries so they can make informed decisions about business. Also, things like machine learning, artificial intelligence, natural language processing created a new set of requirements for how we interact with our data. And the truth is that we just have more data than we've ever had before in human history, and that statement will always be true, which is why I like saying it. So you have intermediate layers like key-value caches and things like that that help us to speed up data retrieval in a lot of different circumstances. But this means our data is more distributed than it used to be. So the first thing we did was we scaled vertically, which means to just bolt more compute power onto the machines that you already have. And this worked for a while until it worked to a degree. But at some point, it no longer made financial sense for a lot of companies to add that last 1%. And so this is sort of like unit economics. The cost of the margin was more than the value that it granted to companies. But even if you had really deep pockets and you're like, I want all the CPU, like just give me all of it, at some point you actually hit the current limits of hardware engineering. What do I mean by that? So the physical limits of hardware engineering, Moore's law is like the most common way to think of it. Moore's law states that roughly every 2 years, the number of transistors on an integrated circuit chip will doubles, which basically means that processing power doubles, just like the size of my kitten in the first 2 years of his life. And like, I know that Moore's law is becoming less and less true these days, but historically speaking, this has been a pretty good way to track the increased processing power. So lucky for us, in the early 2000s came along cloud computing solutions. So of course, we know and love Amazon Web Services, Google Cloud, Microsoft Azure. But you also have, like, if you need to store your data on premises, there are solutions that you can roll out over your existing hardware, like vSphere or VMware, I think, is one of the most well-known options, not the only one. But you can take your own hardware and make it behave like a cloud. So cloud computing gave us an easy way to provision new machines in an on-demand fashion. Like, you get it just in time, just when you need to scale up. Which means that we are no longer constrained by the limits of vertical scaling, because now we can do this thing called horizontal scaling, which means you can take a workload and you can distribute it over multiple machines now. So why might teams want to leverage this ability to horizontally distribute? The first reason is scalability, which means that sometimes you have a machine that can't handle the volume of data you're looking to store, or maybe the request sizes are too big. So one solution is to split that data into multiple chunks by some index, kind of like an encyclopedia. Like, you don't have volumes of encyclopedias that are like one book that's 4 feet long. Encyclopedias are real-life examples of sharding, where you break it into multiple volumes by first letter. So another reason is availability. If you're operating with multiple machines, it means that you gain the ability to have multiple copies of your data stored in different locations. So by having your data served up by more than one machine, we build redundancy into our systems. And the final reason is latency. So if you can store your data physically closer to where your end users are going to be requesting it from, it means that data has to travel over, or like pulses have to travel over less cable, but request times are going to be faster. So now I want to spend a little bit of time talking about modern distributed systems. So you may have come across the term shared nothing architecture before. It's OK if you haven't, but this is the most popular form of network computing. And it basically means that different processes on the same machine don't share access to physical resources. So they don't share memory, they don't share CPU, they don't share devices. Honestly, this is a really reasonable and sensible design, even if it makes life a little harder for lazy programmers like myself who are like, oh, just give me the pointer all the time. Like, no, don't, that's actually bad. So in fact, it's so sensible that the idea of process-based memory isolation is baked into some programming languages by default. In the Go programming language, for example, Rob Pike, who's one of the biggest contributors to the language, said, don't communicate memory by sharing, share memory by communicating. Which basically means have your processes send messages to each other. Don't let them arbitrarily read and write to the same locations on memory that are currently being accessed by other processes. So let's zoom out for a second.
Once again, throw back to that whole idea of what is the point of thread safety? And I thought it was Rust that was like this. John, you might be able to chip in here because you were telling me that you've been programming in Rust. But that sounds like Go is thread safe by default. Is that the same for Rust, or what was the key? Yeah, what was the key advantage of Rust as a program? There was a reason that Rust is considered super cool, and I thought it was because it was thread safe, memory safe by default, or something. Can't memory leak. Fearless. Okay, so Rust is thread safe by default. It's impossible to not be thread safe in. Oh, cool. Okay, and it sounds like Go does the same thing. Is that true, or is that something you understand? Oh. Okay. So you can share memory in Rust, but it's thread safe or it doesn't compile. But Go, you just can't share memory. So they're both thread safe, but one is thread safe for one reason and one it's okay. We'll resume the show. Here we go. Here, we'll keep going.
What does it actually mean to run a distributed system today? Today, I think it's pretty clear to most people in this room, either through some intuition or things that you've run or read about in the past, that building and operating a distributed system is a fundamentally different ballgame than building a system where everything is function calls on the same host in the same process space. But this intuition and this insight wasn't always super obvious. One of the earliest discussions about how distributed computing works, about the fundamental difference here, is the classic 1994 paper called A Note on Distributed Computing by Jim Waldo, Jeff Wyatt, Ann Woolrath, and Sam Kendall, who all worked together at Sun Microsystems. This paper is really neat. It's like a blast of the past. Because in 1994, nobody was building distributed systems at the scale that we see and take for granted today. So a lot of people at that point were just kind of still hand-waving and still theorizing about what these systems will look like. And people were asking, maybe hardware engineering will just solve our problems for us by the time we need to build those systems. Spoiler, it didn't. Probably never going to. So this paper is really worth reading in its entirety if you're interested in this kind of stuff, but I'll try to summarize it briefly for you here. So in this paper, they identify 3 reasons that distributed computing is a fundamentally different beast than local computing. The first is latency, which means the difference between processor speed and network speed, memory access, so this idea of like accessing pointers and locations, and partial failures. I would say that of these 3, memory access has been the one that turned out not to be so much of a showstopper because, like, think back to our earlier discussion about shared nothing architecture. But of course, like, latency has been addressed a little bit by being able to replicate data. You can reduce that delta a little bit, but of course, like, not a totally solved problem. And partial failures is the thing we're going to dig into the most throughout this talk. So according to Martin Kleppmann, like, I think a good summary of these challenges is modern distributed systems look like this. You have a lot of different machines, they're running different processes, and they only have message passing via unreliable networks with variable delays, and the system may suffer from a host of partial failures, unreliable clocks, and process pauses. So distributed computing is really hard to reason about. We've known this since the early 90s. We've probably always known this since, like, this was on the radar, people building computer-based systems. In the 90s, a different group of people at Sun Microsystems came up with, so originally it was 7, but number 8 was added by the Java guy, James Gosling, later on, but 8 fallacies of distributed computing. So to quickly run through them, we know today that networks are not reliable. We know today that latency is not 0, that bandwidth is not infinite, of course, that the network cannot be assumed to be secure, that topology should be assumed, like, we should assume that that will change. We know that there's usually not one administrator. Sometimes there's no administrator. Sometimes we're all the administrator if you don't secure your systems. Sometimes, like, we know that transport costs are not 0, and these days with more and more different devices that are connecting to the internet, we know that networks are not homogeneous. So we're going to dig into this one the most, although all of them are worth discussing, but I only have so much time in this talk. I'm already dangerously close to it. So when I was learning about this about distributed computing, I kind of felt like every new paper I read fenced off a whole category of things that I wasn't supposed to believe in and I wasn't supposed to assume to be true. And I kind of felt at multiple times like, wow, there's so much unreliability. There are so many things that are, like, conditionally true if a very specific, very specific things are true. So how can we know what's even true about the state of the world when we're starting to, start out with learning and building distributed systems? So this actually brought me back. So I studied philosophy in undergrad, and I never thought that I would be talking about my philosophy degree at a tech conference, but here we are. So I actually thought, this is actually an epistemology problem. Like, it almost sounds like an epistemology problem. And epistemology is the philosophical study of knowledge. It's the branch of philosophy that asks the question, so we think we know some things, but how do I really know that I'm in London, speaking at QCon, standing on a stage? Like, how do I know that, like, this is not just an illusion? And broadly, within epistemic philosophy, you have 2 main schools. We have foundationalism, which says that there are fundamental truths about the universe, kind of like how there are first principles in mathematics, and everything else is built on them. Or you have coherentism, the second school, which says that nothing is absolutely true on its own, but when we have enough other interlocking and reinforcing truths, they kind of support each other, kind of like matchsticks can't stand on their own. So in distributed systems reasoning, regardless of which school of epistemology you subscribe to, it's pretty hard to start to define, the basic building blocks of truth. And of course, what if we're all just brains and vats and nothing is real? Skeptics, by the way, you won't find this in philosophy textbooks, but they actually were the world's first internet trolls. Fun fact. So on top of that, so let's go back to message passing for a second. Unreliable message delivery is totally a thing. So another thing in, like, the category of unreliable, like, uncertainties. So the classic case that people talk about is the Byzantine generals problem. So imagine, like, the thought experiment goes, imagine 2 generals, they're trying to coordinate a war, but they can't communicate directly. So they rely on this little unreliable messenger guy to ferry messages between the 2. But the whole time they can't know for certain whether the message actually even came from the other general, whether it was manipulated in flight, whether it was delivered to some wrong place altogether. So this is kind of silly, but this principle actually happens all the time when you're building distributed systems. So we have, of course, like some tools, some technical mitigations, like we have tools to verify the validity of the sender, for example. But we always have to be thinking about things like spoofing and messages being dropped and messages that get corrupted in flight. Of course, we can mitigate a lot of these things by doing a good job of monitoring and observing and tracing our systems, but this is not a talk on any of those things today. I can refer you to other people who can talk about these topics more. So there are a lot of things that we're just never going to be able to know, but we can be certain of one thing: shit's going to fail. Which brings us to the next chapter of this talk, the Cap Theorem.
Cap Theorem.
So the Cap Theorem debuted, dropped, whatever, in the year 2000 when Dr. Eric Brewer from Google gave a talk at the Principles of Computing conference called Towards Robust Distributed Systems. And in the time since, a lot of people on the internet like to write about the Cap Theorem like this. They're like, here are 3 things, you can have 2 of them. Like, you can choose any 2, you can just, like, throw the 3rd one away. But that doesn't really make sense, actually. That's wrong. It's not possible to design a distributed system that way. These days, there are a lot of different alternative frameworks to CAP. CAP is not the only way to think about the trade-offs for distributed systems design. But you should at least think about it like this, with partition tolerance being the constant that we sort of trade off against on either side of. The reason why is you can't sacrifice partition tolerance. Like, that statement doesn't even really make sense. I'll talk about this a lot more soon, but even if you're running a distributed system within one data center, even in, like, one physical host even, you can't
I think
100% immunize yourself against network partitions or partition events. Literally, the only way you could 100% prevent the possibility of a partition is to only have one node, at which point you're definitionally not running a distributed system. And Brewer himself has talked about this in this update, like Cap 12 years later, which came out in 2012. So he acknowledges that, as some researchers point out, exactly what it means to forfeit P, partition tolerance, is unclear. So I realize I haven't actually gone through each letter yet, so let's do that. Let's get a little bit deeper into each part of Cap. C is for, anyone know?
Cat.
C is for linearizability. You're all wrong. It's funny because it doesn't begin with C. So what does this mean? So linearizability is a super narrow form of consistency. It means that, and the word you'll encounter in the literature is register. It means you have an operation to a register update, which you can think of that as like one row in a database. It can only have one value at any given point in time, right? So imagine you have a register update where from time 0, which is before time 1, the cat's state changes from hungry to full. So under linearizability, this means that if any single client saw that the cat is full, from now on, all nodes in the cluster have to return that the cat is full. You're not allowed to show to any client that the cat is hungry anymore. This is really, really hard. This is like ridiculously hard, probably impossible actually. This is a super strong sense of the word consistency because it basically demands instant and universal replication. But replication can't really be 0. Like we know that. There's always going to be replication lag. You at least need like the speed of light. That's your upper bound, like the time it takes for a pulse to travel along some fiber optic cable. But what can we do about this? Well, people who work on databases, of course, spend a lot of time and a lot of energy trying to reduce replication lag. But of course, there are other trade-offs that they have to make along the way. And the final note I want to make here is that eventual consistency doesn't count. So when you have background asynchronous replication, that's not the formulation of CAP. We're not talking about background replication. So there are a lot of different ways to define consistency. And if you haven't seen this blog post before by Kyle Kingsbury on the Jepson.io blog, I really recommend you check it out. So he maps out all the different definitions of consistency that we kind of casually use and what they each logically imply. It's really mind-boggling how many different ways there are to define consistency, like a word that we think we understand. The takeaway here that I want you to walk away with is that consistency is not a binary state. I don't really want to say it's a spectrum because that kind of implies like continuous data, but it's a matter of degrees. There are many different degrees of consistency, so we just have to be really deliberate and careful about which one we actually need to design for. So next letter. A is for availability, which refers to the ability of clients to update data on when they're connected to any node. So we tend to think of availability as being a binary state, but again, like reality is a lot messier because of this wonderful thing called latency. So if you try to issue an update, for example, and you don't get a response for a long time because maybe latency, but maybe like what if that's because the node is down and like your request is not able to be processed at that given point because there's some outage. So latency wasn't part of the original CAP formulation, but it has some really important impacts on detecting and responding to network partitions. It's like a real-world example. Like everyone's got a chronically late friend, right? You're like, oh, well, how long should we wait for our friend before we like give up our dinner reservation? So one way to deal with this in real life and when you're building systems is to set a timeout. So you can just say, I'm only going to wait 10 minutes for my friend to turn up. That's kind of a long timeout for like building a computer system, but determining what constitutes a reasonable timeout is really tricky. And the first time that you set up a system, you have no historical data. Like you might as well just roll some dice. Be like, oh yeah, 12 seconds sounds good. But of course, like monitoring over time is a good way to learn what's normal. You might be lucky enough to pick software that can learn on its own what a reasonable timeout is over time. And the final letter, P, is for partition tolerance. A partition in this case refers to a network partition. I know sometimes this word gets used to refer to the individual like encyclopedia volumes when you're talking about database sharding. That's not the sense that I mean partition today. I mean a network fault or a net split, a partition event, lots of different terms for this. It basically means when you have an event that interrupts connectivity between two nodes of your system that are running either in the same data center, different data centers, whatever. So during a partition event, your nodes might as well be on different sides of a wormhole. Like, there's no way to know what's going on the other side. You don't know if the other side is responding to health checks. You don't know if it's continuing to read and write and process client requests. So let's quickly recap. C is for consistency with an asterisk, availability, and partition tolerance. So the proof of the Cap Theorem is actually pretty straightforward and like not rigorous mathematical proof or anything, but intuitively we can reason that if you have a partition event that happens, imagine this is your like your server setup, you have two nodes in a cluster, which actually is not a good way to design a cluster, but imagine you have two nodes and you have 3 different clients connected, one on the right side, 2 on the left side. A partition happens. You only have 2 logical ways to respond now. Either you let the clients continue to read and write on both sides of the split, but if you do this, you necessarily sacrifice linearizability, because if any updates happen on the green side of the split, the pink client will never be able to see it. Or you pause writes in one side of the partition in one side of the cluster until the partition event ends, which also necessarily sacrifices availability, because the side that's paused won't be able to receive updates. So we'll finish by zooming in a little bit more on partition tolerance and like what is this idea? Why can't I just will it away? So the reason why is because network partition events are inevitable. How inevitable? I'm going to pick on a small startup that probably knows a little bit about this space. So Google, in the first year of a Google cluster's life, it will experience 5 rack failures, 3 router failures, 8 network maintenances, and a host of other hardware-related problems that Jeff Dean has written about extensively. Why, though? Why can't huge companies, like hugely successful companies with lots of smart people, can't just will away hardware failures? Well, hardware is just going to fail. Like, you can't 100% design unfailable hardware. For example, maybe your the routers, like the hardware holding your routers together, mysteriously fails. I don't know. Network cables will eventually just give out. And in fact, apparently, sometimes sharks mistake undersea cables for fish because of the little electrical pulses, and they try to eat them. But it's OK, because some journalists at Ars Technica want you to know that as of 2015, sharks are no longer a threat to subsea internet cables because Google and Facebook lay them, and they wrap them in Kevlar before they go underwater. So the second category of reasons, so anyone who's written software will probably know that sometimes the software we write can do things that we don't expect it to do. And some of those unexpected things will result in events that look like or feel a lot like network outages. So in multi-tenant servers, which is almost always the case for public clouds, we don't have perfect resource isolation, which means that some users can burst a little bit in CPU or memory as they need to. But that's actually a good thing overall. But it can result in this weird case where if you have a process as part of your system running somewhere else on that same host and everyone else is bursting, your process can slow down. It can look like there's a partition event. It can look like there's an outage over there. Some languages have stop the world garbage collection. So if you're running low on memory, we got to pause everything, reclaim some resources so that we can carry on. This causes everything to suspend, which also makes it look like a node is down. And network glitches just randomly happen. This isn't really an illustration of the principle. It's just a character glitch from Wreck-It Ralph, which is a great movie. I recommend you see it. It's about the internet. And also, sometimes people glitch, right? Sometimes people do bad things.
What's the noisy neighbor problem?
Things. So in April 2009, a person took a giant pair, I think it was an axe, actually. I don't know why I drew scissors. Someone crawled into a manhole and chopped through a bunch of fiber optic cables in San Jose. So a lot of people and a lot of data centers in Southern California were on the bad end of a network partition for a little while. So I hope you're convinced, either by this talk or by your own experiences, more likely by your own experiences, that running, building, operating distributed systems is really, really hard. Peter Alvaro, who's a professor out in California, asked the students to think about what's the one hard thing about distributed systems if you had to pick one word. And so one student goes, uncertainty. Peter says, yes, very good, uncertainty. And then another student raises their hand and says, Docker. And the first student's like, oh, actually, yeah, that's better, why not? All right, thanks for coming. No, just kidding. So why does any of this matter? You might be sitting there wondering, OK, that was a good, cool story, bro. Why are you telling me all this? Well, the
Oh, I see. So noisy neighbor is if you are in a multi-tenant architecture system and you're one tenant using your 1% of the CPU and somebody else comes along and uses 99% of the CPU, you're in trouble, right? Okay, that makes sense. Yeah, that's another sort of hardware problem that can arise that has nothing to do with your current existing system design, except for the fact that you're sharing a system with 2 or 3 or 1,000 other businesses.
Practical reality is that we can't guarantee that every node of a system will always be alive and reachable. So it means that some part of every single distributed system will always be at some risk of failure. Think about how hard it is to coordinate plans with your friend who's having bad luck, right? It's that, on a huge scale over and over again with a lot of machines that you can't see them, you can't text them, I think. Maybe you can text machines now, I don't know. But this whole discussion points to the Fisher-Lynch-Patterson correctness result, which is the output of a very famous landmark paper from 1985, which basically states that distributed consensus is impossible when at least one process might fail. So there's quite a bit here to unpack. In the references to this talk, I've linked to more resources if you want to dig further into this. So we've just seen that in almost every case of running a distributed system today, there's at least one element out of your control which represents the possibility for failure. So what can we do about this? We can't will away failure. We can't deny that it's going to happen. But what we can do is we can manage it. We can build for it. So to manage uncertainty, we have a set of technical mitigation strategies. And just like a warning, I'm going to put up 2 pretty high-density slides. I don't expect you to read everything on them. I'm going to hand wave over them a little bit, but they're going to be sent out later. So one category, one genre of strategy is we can limit the amount of chaos in the world by limiting who can write at any point in time. So a very common pattern here is the leader-follower pattern, where you have the leader is the only node who can write new data. Of course, followers can receive requests, but they have to forward those write requests to the leader, who then figures out what order to write them all in. But the challenging part is that the leader is also a node that can become disconnected. So we need a contingency plan to keep things writable in case that node goes offline. So we use a process called leader election to elect a new leader from the remaining nodes who are responsive, and then a failover, which normally has to be like a person needs to say, OK, like that can be the new leader, that's fine. Trigger failover to promote the new leader. Another genre of ways to mitigate uncertainty is to make some rules for how many yes votes from the whole cluster is enough to proceed. So this is a bit of an oversimplification, but these rule sets can generally be thought of as consensus algorithms. Raft is one of many two-phase commit strategies that try to keep a simple majority of nodes in agreement about what's the latest data and what's the latest thing going into the register or the ledger or whatever. So of course, some of them use leader follower inside of them for like extra mitigation. Also, I love telling people who don't know this yet, did you know that Raft doesn't stand for anything? It's called Raft because it's a bunch of logs. Seriously, that's true. And also, I've heard that people use Raft to escape from Paxos Island, which, I don't know, whatever. So what's even harder than getting machines to agree? Like, we've had consensus algorithms. We're coming up with better consensus algorithms every single day. But the thing that we haven't quite cracked is getting humans to agree and getting humans to work together. So I'm going to spend the final part of this talk talking not about computer systems, but on human systems. So here's the thing. The more fault-tolerant we try to make our systems, the more complex they inherently become. When we start adding things to accommodate for distributed failures, like messages being dropped, message queues perhaps, or maybe load balancers and replication of different members of the system, or maybe we can sprinkle a little of our favorite container orchestration, what do you even call this? Container-based workflow orchestration engine. Oh, it's Kubernetes, OK. We introduce complexity into systems. And this complexity is not a bad thing. I'm not saying, like, never use Kubernetes. I'm not saying that. Use Kubernetes sometimes. It's not a bad thing. Like, inherent complexity is something you have to bite to build the systems with the degree of resiliency and fault tolerance that you need for your systems. But of course, like, uncertainty is also introduced by the humans that are operating and building your systems. So Charity Majors talks about this extensively, about this growing complexity. Systems today are getting more complicated. Mental models are getting harder to build. And we are all distributed systems engineers now. So it's getting harder for us to reason about what's going on underneath. So how do we manage this growing complexity? Well, the first step is we need to spend some time understanding where the cognitive complexity comes from. So as we build complex systems out of microservices, out of whatever it is that you want to use, Wood's theorem becomes increasingly important. Dr. David Woods wrote in 1988 that as the complexity of a system increases, the accuracy of any single agent's own model of that system decreases rapidly. So as humans operating big and invisible systems, we all sort of maintain mental models of what we think is going on. So imagine when you first join a new team or you first start to learn a new system, I think we kind of think that we build mental models like this, right? We take a new piece of knowledge and we stack it neatly on top of a piece of knowledge that we had from before. But in reality, we don't always have the time or resources to build those neat mental models. And a lot of the time, like, the context that we're building on top of shifts right from under our feet. So more often than not, we're just doing our best to hang on to the few relevant bits because just like for computers, like humans are limited by the size of your level 1 cache, right? Like I know I am. So the question we're trying to ask when we're building complex systems as teams of humans is how can we achieve consensus with our understandings of the world when a lot of the time we don't even have very good language to compare and contrast what's in our heads? So like in this example, you tell three like software engineers, like, we're going to have fish for dinner. They might have different conceptions of what that actually means. Or maybe they have different mental models about what our systems look like under the hood. Like the systems that we're building and running are really complex. They're more complex possibly than the conscious bit that we can hold in our brains, which makes having conversations about them really hard. So the next best thing we can do is we can try to tease out this information by looking for situations that are information-rich proxies. So incident analysis. Incident analysis is really, really a ripe place for mental model examination. So what is an incident analysis? So usually teams conduct an incident review, sometimes called a postmortem. Although personally, I don't like the term postmortem because it implies that something terrible happened and something died. Like maybe your soul dies a little bit. I don't know. But like nobody died. Maybe depending on your systems, I guess. But like incidents are actually opportunities for fresh conversations and fresh learnings. If you want to know more about this, I really recommend, and I've linked some resources, that you seek out the work that John Ospal and his team have been conducting for the last few years. You can also come to my AMA with Dr. Laura McGuire at 410 today. She knows a lot more about this than I do. But so how does incident analysis tease out mental models? Like, where's this connection? Well, so like during an incident review, there's a couple of typical activities that teams might do. You might like make a timeline of everything that happened. You might create architectural diagrams, try to like figure out the decision trees. Doesn't really matter in the end, whatever format you choose. The goal of this meeting is to create an environment where the team can learn from incidents. The one non-negotiable component of incident review is that it has to be blameless. So blameless discussions focus on learning rather than on justice. So by having these conversations, you'll almost certainly discover that every person in the room had a different idea of what they thought was going on. So just to close down this point on blameless postmortems, I think one really clear litmus test on whether your incident reviews are blameless or not is to listen for counterfactuals. So counterfactuals are statements like, had Denise not put the coffee cup on the table when the cat was out in the room, then the incident would not have occurred. So counterfactuals are difficult because they're hypotheticals. They're like, had X happened, then Y would or would not have happened. So what if you establish that a different course of events could have happened? Like, they didn't. You can't observe them. You can't learn from them. They're not actionable. So here's the thing. Human decisions never occur in a vacuum. The slide is really silly. I miss this little Henry vacuum. We don't have them in Canada. So be Henry, and ask what seemed reasonable at the time. Because all human decisions were formed by some belief that a course of action was reasonable given the circumstances. If you want to learn more about this, I've linked to Courtney and Lex's presentation from SR Econ last year where they do a whole workshop on this. It's really great. So in addition to running your incident reviews in a blameless manner, please keep this in mind. Like, please don't accept human error. Don't say, like, oh, Denise screwed up and that's why the incident happened. Like, don't accept human error as the root cause. So dig deeper, ask harder questions that will actually be more useful. Like, ask, for example, was a user misled by some design that was really unintuitive or really difficult to navigate? Or maybe somebody had too many alerts and they were frazzled. They were experiencing alert fatigue. Or maybe the way that some software was designed didn't take into account the assumptions that a user would bring with them into, like maybe into the web portal, into the control room, whatever it is. And in fact, if you start reading into the latest thinking around resilience engineering, there are a lot of folks suggesting that maybe there are no root causes. One of the best talks on this is by Ryan Kitchen from Netflix, also linked in the notes. So I kind of was half joking about that epistemology thing later. I just wanted a way to shoehorn my philosophy degree into this talk. I'm like, make everyone learn about epistemology. But in all seriousness, we all have different frames of reference, and we don't have great vocabulary to figure out the differences. So of course humans can make mistakes. Like, I think that's just part of being human. But the great thing about humans is that we're also a lot more adaptable than machines. The more we depend on technology and push it to its limits, the more we're going to need highly skilled, well-trained and well-practiced people to make our systems resilient, acting as the last line of defense against the failures that will inevitably occur. This is a paper titled The Ironies of Automation, still going strong at 30. Also a really good read. Check it out. So in pursuit of the socio-technical goals for building microservices, for building resilient systems, for building large, sprawling, distributed systems, we're always taking out a loan against inherent complexity. But we as humans can learn and adapt. That's our superpower. So with this superpower, I challenge you to challenge yourselves to empathize with each and every user, not just the customers, not just the paying ones, but also the ones who are operating your systems, the ones who are going to get paged at 2 a.m. When we think about where to draw the lines for example, for bounded context, those are design decisions, right? Those are not technical decisions, like quote. Those are design choices, and we should always be challenging ourselves to make those choices in a way that optimizes for the humans that operate and build these systems. That means that we should choose tools and processes that promote the things that help humans do their job better. So make sure your tools and processes are promoting learning and sustainable pace. Because after all, we owe it to our end users and to our teams to understand and design for the whole system, including the fleshy human parts. Thank you so much to Nikki Wrightson and for QCon for having me here to talk about cats today, I guess. Again, one more time, those are the slides and references. Thank you so much for listening.
There we go. I mean, standing ovation for that one, right? Because it was so good, so well put together, so good. And I mean, that was my second time through, and I picked up extra things the second time through. Yeah, right? And like, could you imagine again, we should not do like the what if part. I've forgotten even the name of that type of analysis, but like, the non-confirmables, was it, or something? Like it was back here. Anyways, but like, it was just before that. Counterfactuals, no counterfactuals. But like, can you imagine, Josh, if you had seen this just before your system design interview? Like, it's just sort of, it was so easy to follow. It was such a high quality presentation. I learned a ton from it. Her references, again, are, see, there you go. There you go. Got just a little bit better there. And the only other one I wanted to find was she mentioned it might be this one, the retrospectives one, or there was one where she said, like, there are no root cause. What if there are no root causes at all? That one sounded. Oh, there it is. The role of SRE in socio-technical systems. There you go. Oh, that's not a. Oh, it is a. Oh no, it's a podcast. So I might listen to that one later. That one was really interesting. But there is a ton of really cool stuff, and it's actually a good point. I should recommend to you the InfoQ website as well as QCon. Somewhere in InfoQ, there is tons of information. Like if you go through, right, just tons and tons of video, all of a similar level quality, like world-class presentations about computer systems. I've watched about a half dozen of these. I watched this one with Michelle Garrett. She is like a genius, and she talks about how she used. She was working at Condé Nast, so like Vogue and other major magazines, and how they used GraphQL to revolutionize their front end. Anyways, so InfoQ, if you're looking for things and you're just killing some time looking for, I want to watch something about architecture and design today. You can, oh, funny, I clicked the same one twice. Anyways, there are a few that I've watched in here that were really good, so I recommend that. But that is this week's episode of the and we added Flynn's taxonomy when John pointed that out. So that's OS and concurrency. Next week we are talking about object-oriented design interviews. So this one is, we're going to be talking about, I think we'll probably try and talk about design patterns. I think that's important. We want to have a bit of a object-oriented design interview question, if I can find a good one to go across. Otherwise, we'll be just talking about, and John, I think actually your input here with your Java design skills will probably, you would absolutely be welcome back for next week. So anyways, that's the week. I really enjoyed this one because that distributed systems presentation was just so good, and it was also Dr. Bagley was so good. I really enjoyed these ones, so I hope that you enjoyed them too. And we will be back again next week. And thank you for coming. And starting August 10th, I believe. I'm still looking at the calendar. I'm going to be doing, get a copy. I know you've showed it to you before, but one of the things we're about to do at work is we're starting a clean architecture book club. So over 14 weeks, we've got a schedule for reading a few chapters at a time and discussing them. And it'll be in a similar format to this, but hopefully more people talking in the chat here. So I'm going to run one during the day at the office, and we're going to talk about the lessons from the book in terms of the architecture that we have at Zensurance. And so we're going to talk about it in the scope of what we're actually doing. But for the wider Toronto community and global community, now that that's going on, I just hope to talk about the issues in the architecture book, really discuss the content of the chapter, kind of use each other as the social connection for me is really good. I know that we don't get to see all of your faces on this, but I love chatting with you. So it's really enjoyable to have the social aspect. I think the positive peer pressure, sort of to keep each other accountable and motivated to reading the 3 to 4 chapters over the week, so that we can come in and discuss some of the stuff. This is platform agnostic and language agnostic, and so And it's Robert Martin starts. I think he goes back at nearly 100 years in terms of his examination of computing and things and the rules for clean architecture. So it is, these are timeless rules that should be of high value. So if you want to keep coming after the end of this 13 weeks, this is probably where we're going to go next. It's available in the library, so you can get it for free. Yeah, that's right. Yeah. Everything but JavaScript, it's perfect for us. That's right. We're going to need a second one for JavaScript specifically. I hope not. I hope that the rules... You're right, though. You're probably right. I hope the rules are sort of agnostic enough that it works even for JavaScript, because that's where I am right now. But it's about how to design these systems in a way that they are maintainable long term, and how do we reduce the lifetime cost of owning a system and building a system, and so this is, I think this will be fun. If if you don't have a copy, it's at the Toronto Library, and I'm hoping that we get, I think we'll have maybe a slightly larger audience coming forward, because I've invited people in a few other places. And so I also think there will be interpersonal networking opportunities. Hopefully we'll be able to, for John, for your sake, the other 3 people who we've been talking to tonight, I've all worked with them, and we all kind of know each other, and we're friends out in the wild. So it's like, hey, everybody, meet your new friend, John. And hopefully as more people come along from the other communities that I'm chatting in, maybe we have a larger and growing friendship group, and sort of we start making global connections to other programmers around. Maybe some of you talk to each other about, maybe we work together, maybe we find you a job, and stuff like that. So I think a lot of things can, if we just keep doing this kind of stuff, it will be really fun. So that's the week. I'm going to end the show. I'm so thankful that you showed up. This one, the Clean Architecture Book Club, do you mean? This is just going to be right here on the channel. So I'm going to do this live in a chat format, but if there are people who are willing and able to show up who want to show up on camera or want to say something about the week, we hop into Zoom and we'll discuss it live. I just want to leave it open, or you can say your part in the chat, and we'll discuss it that way. So it's sort of and we'll also see how it goes, because it's going to be my first YouTube broadcast of a book club discussion. So, but yeah, it will be broader and widely available. 14 weeks of, anyone can come, or anybody can watch the playback, and maybe I reach out to Bob Martin, and maybe he hops on the Zoom one day over the course of the 14 weeks and talks to us. Who knows? Who knows what happens? We'll see. But that's it. I'm so thankful you came. I'm so thankful that everybody else keeps coming back. And I'm so thankful that, John, that you showed up today. You were really, it was really nice to have you. You really contributed. So thanks. And I'll end the show, and we'll talk to you next week.